Okay, off we go. So here's what we were talking about last time, and basically just going to throw a quick additional comment at this, and that is, we mentioned this last time, but these are very different kinds of fluids. They're importantly different kinds of fluids. For one thing, this kind of fluid up here apparently is just generated, right? Photons, you just make them, here we are, more photons. We're just making photons. Right? You can't do that with a finite amount of gas out in outer space somewhere. We're not making new gas, right? So very, very different fluids. Related. As you spew out photons from your light bulb, in any given region of space, wherever you might be looking at, you're not collecting more photons, right? The photons are not collecting. You're not increasing the density of photons. The density of photons is constant in this story up here, whereas the density of the fluid here is not constant. The density is literally changing. So there's very different sort of parameters of how these fluids behave, and that's ultimately why you get different interpretations of divergence. Up here, divergence is kind of a giveaway of where the fluid has been created. Down here, the divergence is not telling you where fluid's created. You can't create it. It's telling you how density is changing, right? So different interpretations because we're talking about different kinds of fluid. So make sure that you interpret make the interpretation of divergence appropriate to what kind of a fluid are you talking about. And just as a quick FYI, there are some kinds of fluid that where you could do both, where you could have fluid simultaneously being generated or destroyed, right? And also where the density might not be constant. And so I'm not going to, this is not Math219, but I just want to point out, you can still talk about flux and you can still talk about divergence. It's just that then you have two things that those relate to each other instead of this one thing that the divergence just tells you or that the flux just tells you. So anyway, more to say about that in probably like a fluid dynamics class or something like that. Okay. All right. So off we go. We're going to talk about gravitational fields. Y'all may recall from Chapter 3. Here's our formula for a gravitational field. This inverse square radial structure, right, that we talked about way back when. And bad news, good news. The bad news is, and you can see it right here in this expression, the denominator could be 0, at which point this vector field isn't defined. And you may recall when we were talking at some point, very preliminary to all of our Chapter 7 stuff, I pointed out that these theorems are all very delicate, and you can't have singularities. You can't have points where the vector field's not defined. That's just, the theorem doesn't work. Just like with the fundamental theorem of calculus, right? It's very important when you're applying the fundamental theorem of calculus. You can't have singularities or like vertical asymptotes. Y'all remember all that stuff with improper integrals, for example, right? It just absolutely throws nasty wrench into the works. So what are we going to do about this? Well, that's the bad news. Here's the good news. It's got that feature because we're assuming all the mass is at a single geometric point, and that's not a thing. In the physical universe, there are no point masses. The honest formula for the vector field is a little bit different. This being non-physical as it is, the actual vector field does not have this problem. And we're nevertheless still going to draw some conclusions looking at this that I'll get to in just a minute. But I'm just going to wave my hands basically and say, yeah, it turns out this is not going to be a problem for us. I just wanted to address it because it is kind of awkward looking there. Okay. All right, so here's what we're really going to do with this formula. Inverse square radial. Here's a picture of it. And you may notice that picture might look familiar. It is literally exactly this same picture that I drew right here. It's exactly the same picture. Structurally, in other words, this vector field of photons forming a fluid flying out of a light bulb, inverse square radial, just like a gravitational field. Okay, now that's, one could argue, seems like a heck of a nice coincidence. They're certainly unrelated things. Light bulbs are not how gravity works, right? But it remains, coincidence or otherwise, they're structurally identical. The only difference between a light bulb photon flow field and a gravitational field, the only difference is in the value of that K right there. They're structurally exactly the same. So, y'all will recall something I've observed several times in the past is that if something behaves as if a certain thing is true, then you can pretend that that certain thing is true, and you won't get in any trouble. Right, so that's what I'm going to propose here, and this is a really powerful idea, I believe. Gravity apparently behaves as if there are little emitted particles that, mass, don't think of mass as creating some mystical, nebulous gravitational field of forces. Think of mass as just shooting out little particles in the same way that light bulbs shoot out little particles called photons. Right? Structurally, they're the same field, they behave the same. It's as if they're the same. So we're going to pretend that mass shoots out little particles called gravitons. And it would give us, emitted particles. It would give us a vector field just like the light bulb field, which is just like reality. It gives us the exact same vector field. So, now, is this physical? Is this actually true? Well, that's a complicated question, but ultimately, as far as we're concerned, it doesn't matter if this is true. All that matters is reality behaves as if this is true, so we're going to go ahead and pretend that it's true. And it's a powerful tool to allow us to draw some nice conclusions. Okay. All right, so mass emits little particles, just like light bulbs emit little particles. Okay, what do we get out of that? Okay, well, however much mass you have, concentrated near the center of this sphere, the more mass there is, the more mass there is to shoot out gravitons. More mass, more gravitons. And then I argue, gravitons, as they shoot out, eventually have to pass through the surface and thus create flux. So now let's connect the dots again. The more mass you have, the more gravitons you're spitting out, and therefore the more flux you're going to get on your boundary surface. And so the nice little final punchline then is that the amount of flux of gravitons flowing through space, through your surface, that amount of flux is proportional to the amount of mass that there is on the inside. That's a really powerful conclusion. It's extremely not obvious if you take the sort of forces point of view. If you look at this vector field and try to write down for an arbitrary closed surface, it's a very hard problem. But you just take this little kind of cheap little hack, little point of view, and it becomes, dare I say, obvious. More mass, more gravitons, more flux. Y'all okay with that? Willing to believe it? Okay. All right. Now, what's the deal with this constant right here? Why negative 4 pi g? That's just the proportionality constant that it turns out to be. This is a matter of some arguments that I'm going to say we don't need to worry about in this course. So I'm just going to assert that that's what the right constant is. Yeah, don't worry about it. Okay. All right, now that constant, negative 4 pi g, you see there and there as well. And now if we look at this equation, notice it just says mass is a triple integral of density dV. Other than that multiplicative constant, which is on both sides, it's perfectly legal. This is just an observation that mass is an integral of density. Old news. We knew that a long time ago. And then let's look down here. This is just our recent theorem. This is our Gauss's divergence theorem that says flux is a triple integral of divergence. And so this being an old argument, this being a consequence of this graviton crutch that we're using, and this being Gauss's divergence theorem, the punchline then is that these two triple integrals must be equal. And now, I appeal to your mathematical intuition. We got two integrals. And over any solid, whatever that solid might be, these integrals always give you exactly the same result. And I think that's pretty convincing that these two integrands must have to be equal as well. Okay, so these are our two kind of, I'm going to say, big results that we get, again, mostly from this graviton point of view, that mass is proportional to gravitational flux through a closed surface, specifically the amount of mass on the inside of the closed surface is proportional to the gravitational flux. And then likewise, the divergence of the gravitational field that's created is proportional to the mass density. So, neat, two nice, little, very non-obvious results. And let's just talk for a moment about how non-obvious it is. Now you're going to see, for the gravitational field, you see this formula and you think, well, that doesn't look that bad. But let me just remind you, this formula here only works for a single little point mass. If you have mass distributed over some space, right? Like if you're talking about the gravitational field created by a planet, for example. There's a lot of mass. There's a lot of pieces of mass. And this little piece of mass right here creates its own gravitational field. And this little piece of mass over here, it creates a different gravitational field, pointing in different directions at a point in between them, for example. So altogether, when you consider the gravitational field created by an entire lump of mass, there's infinitely many chunks, each of which is creating its own gravitational field. Computing that vector field is actually bonkers inconvenient. It's a lot to write down, and it's a tough calculation. So I think it's a really powerful result that even without computing that nightmare of a gravitational field, we can compute its divergence in a snap with this clever little graviton argument. So very, very clever. So again, props to the graviton argument for letting us see this, and to Gauss's divergence theorem. That's the necessary sort of, in order to ultimately connect that top to this bottom, we need to be able to make this connection right here. So Gauss's divergence theorem is also critical to this strategy. Is that cool? Okay, who cares? A lot of people make the point that gravitation, unless you're an astronaut or a cosmologist, right? Gravity's a constant where we live, pretty much, right, at the surface of the Earth. So who needs to worry about all these sophisticated ideas? And there's a case to be made there. But here's the next observation I want to make. The next argument I want to talk about is suppose you're interested in electric fields. Now, electric fields, all engineers have to understand electric fields. Electric fields are in every piece of electronics, right? Kind of a big deal, right? It's a real serious thing. Electric fields, as y'all will need to work with them, are not just constant, right? Very much so not constant. So we are going to definitely need to be able to understand electric fields, and here's the beauty of the situation. They, too, are inverse square radial. That means that electric fields are structurally the same as gravitational fields. Which means that any intuition that you have about gravitational fields, well, it's just different constants. But all the ideas and all the way that you connect the dots up here concerning gravity, all the same stuff works for electric fields. So my position is and has been for a long time that the best way to understand electric fields is to understand gravitational fields, because they're the same thing. You know, aside from, different physics, I suppose, and, different constants involved, but in terms of the big ideas, it's all the same stuff. And so, so that means that electric fields being just like gravitational fields being just like light bulbs sitting there shooting out these little particles, right? You can literally think of electric fields, and I encourage you to do this. You can think of electric fields as just representing the flow of little particles, whatever you might want to call those things. You're going to want to call them electrons. You can't call them electrons. That's a different thing, right? That's no fair. I've heard them called photons. I don't really know enough about the physics to accept that. So anyway, all the same ideas work. And so, for example, in the same way that mass is basically shooting out gravitons and therefore creates gravitational flux, or flux of the gravitational field, likewise, charge is shooting out little particles which create, whatever these little particles are that communicate electric fields, which then create electric flux, or flux of the electric field. And then again, density argument, write down the divergence theorem, hop, skip, and a jump. These two integrals have to be equal, therefore the integrands have to be equal, and we get another extremely not obvious result. I guess you could say extremely not obvious pair of results here. That electric charge inside of a closed boundary surface is proportional to the electric flux, and likewise, the charge density is proportional to the divergence, aka the flux density. Oh, really nice results. By the way, these are both what I'm going to call Maxwell's first equation. These are two different versions of Maxwell's first equation. And they look different. They look pretty different, right? One's about flux, one's about divergence, one's about charge, one's about charge density. Seem to be the same statement. They seem pretty different, right? But two cases that I'm going to make as to why we should view these as being the same. One is Gauss's divergence theorem is the immediate connection between them. Right? That's boom, one step, right, to relate these two equations to each other. And then here's the other one. If you kind of just think about how this rolls off the tongue. Charge is proportional to flux. Charge density is proportional to flux density. They say the same thing. It's just that one of them has the word density stuck in there. They're really, really very similar statements if you interpret appropriately. Interpreting divergence as flux density. Charge flux, charge density, flux density. Very closely related. Okay. All right, so again, two separate equations, but morally kind of the same equation in some sense. Okay, how are we doing? Everybody okay? Okay, moving along. Okay, so new theorem we're going to develop. This is called Stokes's, sometimes called Stokes's curl theorem. It is a kind of a ripoff of ideas that we've been developing. Let me just remind you the situations that we've done morally the same ideas. Fundamental theorem of calculus, right? Changes in accumulating quantity, blah, blah, blah. Fundamental theorem of calculus. Fundamental theorem of line integrals. Green's theorem. the other Green's theorem, the one with divergence, Gauss's divergence theorem. We've seen 5 previous examples of what I'm going to call, arguments that involve boundaries and accumulation and densities. Right? The same kind of ideas, different details appropriate to the context, but the same basic ideas. And that's exactly the pattern that we're going to follow here for Stokes' theorem. We're going to talk about boundaries and what our convention is going to be for boundary orientations. We're going to make an observation about accumulation. That's going to be really, really familiar. I'm going to wave my hands at making this case that even though you compute it on the boundary, you should really think about it as actually being distributed over the interior. And therefore it behaves like a stuff. And when you're dealing with stuff, you can talk about stuff per unit size. The stuff is circulation. The size is area. And with those pieces, we fit the pieces together and bam, theorem. So now you probably noticed the layout of how I put the pieces together here. Doesn't that look familiar? Just if only the layout on the page is structurally just like when we were doing, for example, Green's theorem. And you're going to notice a lot of the rest of this follows it's very reminiscent of those theorems we've already done. So please do keep a strong lookout for that. In fact, I would encourage you after today's lecture, it'd be a great idea to do one of these, where you're looking at Green's theorem in your left hand, what we're doing with Stokes' theorem here in your right hand, and just compare and contrast. And notice, wow, they're really practically the same thing. Just Green's theorem is 2-dimensional, Stokes' theorem is 3-dimensional. Other than that, it's really very, very similar. And, details different appropriate to the circumstance. Okay, so let's not get ahead of ourselves, though. Let's do all the appropriate setup. First, let's talk about what boundary orientations are. Again, this is arbitrary. Again, arbitrary doesn't mean a free-for-all, right? It's arbitrary, but it's standard, so not optional. The arbitrary convention is that if you have a surface, and that is specifically an oriented surface. Keep in mind, an orientation on a surface tells you which direction is the chosen direction through the surface, right? Perpendicular to the surface. Okay. Given an oriented surface, we can talk about the boundary. Now, the boundary of a surface is going to be a curve. Imagine a piece of paper, for example. Right, here's a piece of paper is kind of a surface. That surface has a boundary. The boundary is the edge of the paper, namely, it's a curve. Right? All right, that boundary curve. Well, there's 2 different ways I could orient that boundary curve. I could say, let's go that way, or I could just as well say, let's go this way. Which one do we do? That's what we need to set up a convention for. Here's the answer. The answer takes a little bit of doing. It's not quite as simple as the examples we've seen in the past that were, counterclockwise, pretty much, outward. We've had some very simply phrased answers. Here it's a little weirder. It's just the nature of the circumstance. But here's what we do. Step 1, look at your surface normal. In other words, look at the orientation of the given oriented surface. Use your right hand. Point your thumb in the direction of the normal. Look at your fingers of your right hand. Notice that they kind of point in a direction, I'm going to say, around your thumb. Right? Again, right hand, thumb. Your fingers point in a direction around the thumb. And that defines what I'm going to call a swirl. Like so. That swirl, so indicating a direction that kind of you imagine like a rotating, like imagine there's a little hurricane on the surface here, right? That swirl if you were to drag this whole picture close to the edge, where it kind of starts to touch on that boundary curve, it's going to do what I call side swiping the boundary curve. And in particular, in this case, notice that it side swipes that way. Right? How this purple swirl, how that sort of, when that butts up against the boundary curve, it's pointing that way. And that is that is our orientation for our boundary curve. Is that cool? It's arbitrary, right? But this is a highly standard and meaningfully useful convention. Does everybody understand? Is everybody happy? Okay. All right. So that in mind, what's our accumulating quantity? Again, we're going to be doing making an accumulation argument. So we need there to be an accumulating quantity. I claim boundary circulation. Now, again, flashbacks to Green's theorem. When we were developing Green's theorem, same accumulating quantity, boundary circulation. So in some sense, we kind of already know this is going to work. And so you can see it right here in the picture. If you take a surface and if you cut it into two pieces along that new edge, well, as part of the boundary of the left side, that new edge is going to be oriented that way. Normal, fingers, swirl. Side swipes going that way, right? But as part of the boundary of this side over here, it's going to be oriented that way. And same argument now. Normal vector, fingers, swirl, and that swirl side swipes that way on that same edge. And so you notice, same edge, opposite orientations, they cancel. It's the same thing that we saw with Green's theorem. Just kind of, sitting up in space as opposed to, down in the plane. Does everybody buy it? Okay. All right. So again, I think it's really helpful, really worth your time to, go ahead and compare with Green's theorem. Just flip back to section 6.2. We drew a very, very similar picture. And take a look. Okay. All right. Now, again, I claim whenever you have an accumulating quantity, you can always think of it as happening in the interior. After all, it's something that I define for my piece of surface. We have an accumulating quantity for a piece of surface. That accumulating quantity accumulates in the sense that if you cut up that surface into little pieces of smaller surface, then the whole is the sum of the parts. So the surface is the thing. Now, the fact that you happen to compute your accumulating quantity on the boundary is, whatever. That's an illusion. That's a distraction. It's not the point. That's not where it happens. We're talking about a quantity that is defined for the surface. You should think of it as being in the surface. And so like any other accumulating quantity, the quantity on the whole surface is the sum of, whatever that quantity is for that piece of surface, plus whatever the quantity is for that piece of surface, plus whatever the quantity is for that piece of surface, etc., etc. Think of it as happening in the interior, even though you're measuring it on the boundary, and we've seen several, I hope, persuasive examples of where that really makes sense in other settings. Okay. All right. So we're going to imagine boundary circulation as being a kind of a stuff, like any other accumulating quantity, like mass or ants or whatever else that we're adding up over some surface. Okay, and with that noted, we have this idea of a density, right? Circulation is a kind of a stuff, therefore it has an associated density. There's the question of how much of the stuff there is per unit size. Size being area, because that's what we're looking at. A surface. Surface comes with an idea of area. So stuff per unit size, that's all it is. It's a weird kind of stuff, granted, right? The stuff, the accumulating quantity being circulation, is why we call this circulation density. Again, flashbacks to Green's theorem, right? When we were developing, right as we were getting ready to state Green's theorem, we wrote down some very, very similar ideas. So again, do that comparison, do that side-by-side comparison, and you're going to notice, we're just ripping off Green's theorem here. Okay. Now we do get a different formula for our circulation density. The formula is this. And the reason we get a different formula is because we're in a different context. We're talking about a three-dimensional vector field, not two-dimensional. How it points upward or downward, that third dimension element of it matters, right? We're also going to find that the orientation of our surface, this little n, also matters. And I'm going to be able to do a better hand wave later, but the circulation around the boundary of a little piece of surface oriented like so, I don't think it's too surprising that boundary circulation would be different from that boundary circulation. Other way, sorry. Because it's a very different piece of surface, and it's sitting in space in these very different ways. All right, anyway, that's the formula as it turns out. Again, that's details. Okay, let me rephrase that. It's very important, mathematically, but that's not, we're not here for doing all the rigor, right? And so I'm going to sweep that under the rug. I think rather than the computation of this formula, far more important to understand this idea that we're talking about an accumulating quantity per unit size, and to understand that this is literally circulation per unit area. That's what you're going to need to. 10 years from now, when you're trying to apply Stokes' curl theorem, much more important to understand this interpretation. This formula you can look up in a book. Okay. All right. Okay, we're ready to put it all together. Just like with Green's theorem. Circulation, boundary circulation is the object of interest. That's what we decided to call sigma, and that we're going to study for whatever reason. And then next, we made the case that it's an accumulating quantity. The whole is the sum of the parts. Again, that reads right off the equation. The whole is the sum of the parts. That's all that's saying. And then we put it together. That little part, each little piece of circulation, we're talking about a little piece of circulation for a little piece of surface. Stuff is stuff per unit area times area. Right? So we had this previous, on the previous page, this idea of there being circulation density, and I assert that this is the formula for it. And notice we're done. We have ourselves a brand new theorem. This boundary circulation can be computed with a surface integral. That's Stokes' curl theorem. Everybody with me? Now, real quick, hop, skip, and a jump. I'm going to point out that don't forget we've already made this little. You could call it a notational little shorthand, but I actually think this is better than that. But in our orientation unit normal times our ds scalar, we've previously rewritten that as the ds vector, and notice that. And I think this is an important distinction that allows us to rewrite our theorem as I have it already highlighted here, like this. And that emphasizes, again, what I think is an important point, that this is not a scalar surface integral of a quantity that involves a dot product, but it's better to think of it as straight up, very simply, a vector surface integral. and our integrand is curl. Right. All right, so this is how I'm going to prefer to write Stokes's curl theorem. Everybody with me? Everybody notice how we put the pieces together? It's just exactly like Green's theorem. And again, please do that back and forth A-B kind of comparison between the two. Okay. All right, let's do an example. Let's see here. Here we go. And this example is not that different from our first example of Green's theorem. We're computing a vector line integral. We have a curve given, pre-parametrized. We have a vector field given. Given a curve, given a vector field, compute the vector line integral. Okay, now I remind you, when you are asked to compute one of these things, you have various tools in your toolbox. You do not have to use, unless the problem specifically says so, right? You don't have to compute in, obvious ways. You're allowed to rummage through your toolbox and try to find the right tool for the job. And you really should use the right tool for the job, of course. So now, in terms of presentation, you notice the curve is given parameterized. We have a formula for how to compute a line integral using a parameterization, right? Pulling back through the parameterization. And you might be tempted to do that. You might be tempted to say, all right, look, here's X. Here's Y. Here's Z. Take those and plug them into the vector field and compute dx as x prime dt and, do that whole thing. And what you're going to find is that you get some ugly trig integrals. And all else being equal, not nice to... they're doable ultimately, but you don't probably want to. And reasonable not to. Okay. All right. So, let's think more creatively on this. I'm going to note that we have, of course, our brand new theorem. We've been asked to compute a vector line integral. Our brand new theorem involves a vector line integral. Wouldn't it be nice if we could therefore apply Stokes's curl theorem? Now, I have a warning. There's a landmine, very important landmine. You might even be able to see this coming. I made a big, dramatic deal about this for Green's theorem, and probably for a couple other of the theorems we've talked about. Here it is. It says so right here in the theorem. Stokes's theorem only applies to boundaries. So I need, very importantly, to establish that this curve, it had better be a boundary. Else you cannot apply Stokes's curl theorem. Yes, question?
So just semantics-wise,
yeah.
I understand that the double integral is basically saying something. We proved that curl dot n is the same thing as circuit flux.
Yep.
Right? So you're summing up all the individual pieces of flux, etc.
Yep.
But the question is compute the line integral on the curve. So I'm just
Yeah.
probably missing something, but where is the gap being bridged? Are we computing?
That's the magic of... No, I hear you. I totally hear you. It feels like no fair because the question says line integral and we're talking surface integral, and that just seems no fair, right? That's the beautiful thing about Stokes's curl theorem. It just happens to be that when you view circulation, keep in mind this boundary line integral is a circulation. When you view that as a quantity and you think about how that adds up over the interior accumulation aspect of things, then what you end up with is a surface integral, even though the quantity itself is a line integral. That's just kind of the sort of unexpected weirdness of the theorem. And now if you look back to Green's theorem, I claim you're going to notice the same thing, right? Because Green's theorem is initially about circulations, right? And yet we compute it with a double integral, right? Yeah, so it's totally the same deal. Yeah, absolutely. So you're right to be uncomfortable with that. Yeah, totally. Okay, so now let me remind you again, I think this is a very dangerous landmine. I don't want, I want as few students as possible to step on this landmine. But I get more and more dramatic every year trying to, the more dramatic I get about this, then the less students step on it. But I'm not down to 0 yet. I'm aiming for 0, right? So very, very importantly, this only works if your curve is a boundary. It's got to be a boundary. Now, there's 2 takes that I'm going to give you on this as to why this matters. One is, look back at how we developed the theorem. We had an accumulating quantity. It's very important that the accumulation works. That's where the theorem comes from. And if you look back at why it works because we're talking about boundary circulations. Right? So the whole thing is premised on this being a boundary. Right? But now, a little bit more bluntly, it's only if this curve is a boundary of a surface that I even have a surface over which to even talk about a resulting flux integral. Right? So just like with Green's theorem, this is not some sort of fine, fussy, picky condition about regularity or something little subtlety like that. If your curve isn't a boundary of a surface, there is no surface to even talk about a double integral. So it's not that these 2 integrals exist and just don't happen to be equal. It's that there is no double integral because there is no surface, right? So if again, and I see this, oh my God, so much, and aiming for 0. I'm hoping to get this, out of the experience of students. If you have a line integral that's not a boundary, and if you start talking about double integrals of curl, there is no such integral because there is no such surface because your curve is not the boundary of anything. Right? So very, very important. I think that's enough of a discussion of the whys. But now let's get to the how do you tell? And here we go, looking at our curve. Here we go. So our curve, like that. There's our curve. Note the minus sign. By the way, remember all the discussion we did at some point in the past about how, that minus sign represents a reflection, and of course cosine t, sine t, y'all recognize, and I hope y'all can think through the various tools we've discussed and persuade yourself that this is this unit circle in the xy plane oriented like I have indicated here. Make sure you're good with that. You're going to think it through. There's some subtleties in there. Make sure you're good with that orientation. And is this a boundary? Okay, well, tempting to say that it's the boundary of that disk right there that I have in green. And but here's the problem. We need to know that this curve, this oriented curve, after all, it is oriented. We need to know that this oriented curve is the boundary of this as an oriented surface. So I need to decide which direction do I want to claim this green surface S is oriented. Is it oriented up or is it oriented down? And the way we proceed on this is we just entertain options. If I were to orient it upward, let's play the game. Upward orientation on this surface. Thumb. Right hand, right? Right hand, thumb in the direction of that orientation. You look at the fingers, that gives you a swirl. That swirl would kind of go around like that. And that's going to sideswipe in this direction, which is the wrong direction. So I guess we guessed wrong. Right? So, okay, all right, well, let's try the other way then, just for the sake of, completeness. let's suppose we try orienting down. Right hand, thumb in the direction of that orientation. You look at the fingers of your right hand. Which way do they rotate around your thumb, aka around that normal vector? That makes a swirl kind of like that. And that sideswipes in the correct direction. So there you go. There's your orientation for your surface. And indeed, our curve is the boundary of that oriented surface. Everybody see how that works? You just trial and error. Look at your two options. See which one works. One of them is going to work. One of them is not going to work. And if you guess wrong the first time, well, then you'll guess right the second time. We good? Good deal. All right. So, it's all downhill at this point. We just agreed that our curve is a boundary. Being as it is a boundary, boom, Stokes' curl theorem right there. Just write it down, just copying from above. And I can, this initial circulation I was interested in, now apparently I can compute this as a flux of this curl, and now it's just kind of plugging stuff in and noting how easy life becomes sometimes. We will observe that the vector field, you got to be able to compute the curl of that vector field. So now make sure you're good with this. Make sure that you remember all these formulas from Chapter 3. If you plug into that Chapter 3 formula, compute the curl of that vector field, you'll get 0, 0, 2. Make sure you can do that. There's a fair amount of partial derivatives and which one minus which other one, and a lot of little details. Make sure you get that straight. Our normal vector we just discussed, right? Our normal vector is 0, 0, negative 1. And it's all over but the shouting. The dot product is really easy. The dot product ends up being a constant. It factors out. We end up with an area of a barnyard variety geometric figure, and bam, answer. And we win. All good? All right. Okay, let's see here. Now I've got a few minutes left. Or actually, let me not say plural if it's singular. Okay, yeah, I have singular, 1 minute left. Okay, I just want to plan a quick thought, and then we'll fill in the details next time. So when we were talking about the fundamental theorem of line integrals, which we initially wrote down like this, we then observed that TdS was just dx, and that allowed for restating the theorem like this, which allowed us to reinterpret change as an oriented size. We just kind of made up that idea of an oriented size, dx, and therefore interpreted gradient as being an oriented density. And I claimed that we were going to encounter a morally equivalent idea eventually, and here we are. So here's the exact same structure of ideas. Here was our initial Stokes' theorem. We rewrote in ds as ds vector. We then rewrote Stokes' theorem like that, which reinterprets for us d sigma like this. And what we're going to do next time is we're going to understand ds as being an oriented size, as such curl as an oriented density. And this is going to be the foot in the door that helps us make geometric sense out of what does that thing look like? What does curl look like in the pictures, right? How do you visualize that? Which way is it pointing? Stuff like that. It's going to come out of this idea of interpreting the oriented density. Y'all have a good rest of your day. We will pick up here. Well, we'll pick up here on Wednesday. Have a good one. Don't forget about attendance.